What is deadlock? In multi-threaded application, there may be some situations where one thread is waiting for a resource that is locked by another thread, and that another thread is waiting for another thread as well, and so on, until this dependency loops back to the first waiting thread. Hence, this results all the threads are waiting for each other to release the resources to progress and blocked forever in the process. As a more concise explanation, a deadlock occurs when a thread is waiting for an object lock that is acquired by another thread, and second thread also waiting for an object lock that is acquired by the first thread. As both threads are waiting for each other to release this condition, this scenario is called deadlock in multithreading. For example, thread A holds resource 1 and waits for resource 2, whereas thread B holds resource 2 and waits for resource 1. In this case, both threads are blocked condition that will never progress. What scenarios can cause deadlock? Nested synchronized block will reverse the ordering of objects. Calling one synchronized method from another where methods are not using the same object to synchronize. How can we avoid deadlock situation? Deadlocks can be prevented by eliminating the 4 required conditions, which are named as from mutual exclusion, resource holding, no preemption, and circular wait. Mutual exclusion is also known as mutex, is the simplest type of synchronizer, and it ensures that at the most one process must execute the critical section at a time. To ensuring access to the critical section, the thread acquires the mutex, executes the code, and then releases the mutex. Thus cause all the other threads block till the mutex releases. The main notion of mutex concerns ownership. Only one thread can own the mutex at a time. If a second thread tries to acquire ownership, it will be suspended until the owning thread releases the mutex. If several threads are waiting to acquire the same mutex, they will all be released simultaneously when the owning thread releases the mutex. The released threads will then have a sort out amongst themselves who gains ownership. By acquiring a mutex at the top of a code block and releasing it at the bottom, we can provide thread safety. Several discontinuous code blocks can all acquire and release the same mutex, in which case all this code is considered to be on the same monitor. Hold and wait. Hold and wait is a process occurs if the thread is requesting additional resources that are being held by others while currently holding at least one resource. The hold and wait condition states that the process is holding on to resources that may be required by other processes. The main point here is that the process is holding on to those resources and will not release them until it gets access to the requested resource, which are being held by other processes. There are several possibilities for this. If all processes request all resources at one time, and if a process needs to resource only in its early execution, it doesn't need to for the rest of the time, which can cause the waste of system resources. Or as another case, if processes holding resources must release them before requesting new resources and then reacquire the released resources along with the new ones in a single request. This can be a problem if a process has partially completed and operating using a resource and then fails to get it reallocated after releasing it. The hold and wait or resource holding conditions may be removed by requiring processes to request all the resources they will need before starting up. This is difficult to satisfy and in any case inefficient use of resources. Another way to satisfy is the required processes to request resources only when it has none. First, they must release all their currently held resources before requesting all the resources they will need from scratch. This is often also counted impractical because resources may be allocated and remain unused for long periods. Also, a process requiring a popular resource may have to wait indefinitely, as such a resource may always be allocated to some process, resulting in chaos, resource starvation, which is a special type of deadlock. And also, hold and wait and circular wait are conditions that are met in can cause deadlocks. No preemption means there is no mechanism for freeze the resource if one thread holds the lock for a specific period of time. Preemption of process resources when it's possible can prevent this situation, but also the no preemption condition may also be difficult to avoid as a process has to be able to have a resource for a certain amount of time or the processing outcome may be inconsistent. Preemption of a locked out resource generally implies a rollback, and because of the overhead cost, it should be avoided, whereas algorithms that allow preemption include lock-free and wait-free algorithms, and its optimistic concurrency control can be considered. One applicable approach could be while a process requires a new resource, firstly it could implicitly be forced to release all the resources previously held and then forcing the process to reacquire the old resources and the new resources in a single request. Another approach is that when a resource is requested and not available, then the system detects that what other processes currently have those resources and themselves blocked waiting for some other resource. If such a process is found, then some of their resources may get preempted and added to the list of resources for which the process is waiting. The circular wait condition states that there exists a chain of processes where each process is waiting for a resource that is being held by another process. In this condition, it doesn't have to be mean that the process is holding onto a resource that the other resource is requesting, but it means that all processes are waiting for a resource that is being held by another process in a chain. During runtime, a chain occurs in which two or more threads are each waiting on the other thread to free a resource that is locked. One way of approaches that avoid circular waits include disabling interrupts during critical section and using a hierarchy to determine a partial ordering of resources by number of all resources to require that processes requires resources only in increasing and decreasing order. One of the challenges in this method is to determining the relative ordering of the different resources. If no obvious hierarchy exists, the memory address of resources can be used to determine ordering and resources are requested in the increasing order of the enumeration. Algorithms like Dijkstra can be applicable. Avoiding nested locks, avoiding unnecessary locks, and using thread join. So additionally to preventing deadlock, we can use some of these methods as well. Deadlock occurs when we provide locks to various threads, so we should give one lock to only one thread at a particular time to avoiding nested locks. So acquiring and releasing the locks need to be managed properly to avoid confusion. So we must avoid using the unnecessary locks if it's not required. Thread join helps to wait for a thread until the thread doesn't finish its execution, so we can avoid deadlocks by maximum use of join methods. Generating or analyzing thread dumps. Visual VM is widely used for detecting deadlocks and generate thread dumps. After integrating with the Visual VM plugin with our IDE, we can easily run the application by Visual VM run button and check the result. It helps us in analyzing threads performance, thread states, CPU consumed by threads, garbage collection, and much more. If the deadlock occurs, it explicitly informs the user on the Visual VM IDE. To generate the thread dump, we can easily click the Generate Thread Dump button to see the logs. On the other hand, gstack is a very easy way to generate a thread dump is widely used by the developers. We don't need externally use a plugin to set up GStack, which internally exists in the JDK. To use the GStack from command prompt, first of all, we need to start our application by running from IDE. We need to run GPS mv command to learn the process ID. Then we can simply get the thread dump by running the gstack l process ID command to get the result.